Deferred classes will enable us to describe abstract concepts independently of any implementation concern. They will also enable us, as we're going to see, to express the common elements which underlie a number of implementations of the same basic concept. For example, we might have the notion of lists and many different possible implementations of lists. Well, we can have a class list that captures what is common to all of them and that captures the notion of list independently of any particular choice of representation. The terminology is going to be the following. A class or a feature can be deferred, meaning that it's abstract. It's specified but not implemented, or in the case of a class, not fully implemented. If it's not deferred, we will say that it is effective. So effective simply means the reverse of deferred. It means fully implemented. And again, this applies to both features and classes. So a class or a feature is either effective, meaning implemented, or deferred, meaning not fully implemented. This concept is going to have quite a few applications. The four main ones are listed here. They provide us with an abstraction mechanism to describe concepts at a high level. They provide us with a taxonomy mechanism in order to classify a number of variants of a certain notion in a clear and understandable way. They enable us to capture common behaviors when we have a set of implementations of a common concept, and they will also provide us with key mechanisms for high-level modeling, analysis, and design of systems, which is one of the strong points of the object-oriented approach. Here's a typical example of the use of a deferred feature. In class list, we are going to have a feature force which describes how to advance the cursor. So the class list describes a general notion of list independently of any particular implementation, such as those which I just mentioned. However, the general idea behind lists is well known. It's the idea that we've seen in previous lectures. You remember, I'm sure, that we have this notion of cursor, which doesn't have to be part of the object. It could be external, but that doesn't change the picture. We have queries like count, which gives us the number of elements in the list. We have query after, a Boolean valued query, which tells us if the cursor is after the last element, and before, which tells us if the cursor is before the first element. And the general idea regarding the cursor is that it can be on an element, or it can be before the first element or after the last element, if any, but it cannot be any further. It cannot be before the position before the first element, and it cannot be further than one position after the last element, if any. So that's the condition on the cursor. Now, you remember, I'm sure, that we also have a command force, which advances the cursor by one position. The presence of force is a characteristic of the class list. The implementation of force will be different in every one of the descendants, like, for example, arrayed list or linked list, which implement different representations of lists. But the idea that we have a force feature, a force command, is common to all of them, and so it should correspond to a declaration in class list as shown here. However, we cannot give the implementation. That would depend on the choice of representation. So for that reason, instead of the usual do clause that you know from other routines, here we have the single keyword deferred, which basically says this is an important feature. It should be declared at the level of this class because conceptually it belongs here, but I'm not ready to give you the implementation now. The implementation will appear in descendants, in effective descendants, that is to say, fully implemented descendants. What's also important to note here is that although the feature is not implemented, that doesn't prevent us from saying interesting things about it. For example, it has a precondition and a postcondition. The precondition tells us that if we want to be able to apply force, we can be on an element, or we can be, for example, on the last element, but we should not be in the position after the last element, because then we would have to advance the cursor by one position, and we would violate the basic condition about the cursor, which is that, as noted a few moments ago, it's on an element or just before the first or just after the last, but no further. So we can have this precondition which says require not after. And we can also have, and we should also have, the postcondition which characterizes the abstract but precise effect of force on the cursor by telling us that the new index after a force will be equal to the old index, that is to say the value of index before an execution of force plus 1. So you see how interesting and powerful this mechanism of deferred features is. It enables us to describe that a certain functionality is needed at a certain level of abstraction, here class list, without having to say how it is going to be implemented, but with all the relevant properties, the relevant formal properties in the form of a pre and a post condition that apply at that level of the discussion. We have deferred features as just illustrated, and we also have deferred classes. The definition of a deferred class is very simple. It's any class that has at least one deferred feature. In our example, we had this feature force, which was deferred, and actually we're going to have a couple of other deferred features, but one is enough to make the enclosing class list itself deferred. So that is the definition. A class is deferred if it has at least one deferred feature, and there are two consequences, two rules that follow from this definition. The first one is that if a class is deferred, as per the previous definition, that is, it contains at least one deferred feature, then it cannot be declared as just class something, for example, class list. It has to be declared with the keywords deferred class at the beginning, not just class. So this is going to be how list, for example, appears in its declaration, deferred class list. And the second rule is that such classes cannot have instances. You know that given a class, we can in general create an instance of that class with an instruction like create X, where X is declared of the corresponding type. Well, if X is of type list, which is a deferred class, create X is not valid. It will be rejected by the compiler. Assuming that list, which is deferred, has a descendants such as linked list, which is effective, the plus will be ineffective, and arrayed list, which also is effective, then what you can do is create y.make, where y is, for example, of type arrayed list or of type linked list, that is to say of a type which is an effective descendant. But you cannot directly use X to create an object of type list, a direct instance of type list, and the reason is easy to understand. Since the class has some deferred features, you might end up trying to apply an operation to an object like force, where the object does not have any implementation of that operation. On the other hand, in effective descendants, because these descendants are effective, they need to have implementations of all the features, so that it's okay to create a direct instance of linked list or a direct instance of arrayed list. What's interesting in a deferred class is that nothing requires it to be completely deferred in the sense of having only deferred features. It's perfectly possible, in fact quite common, for a deferred class to have a mix of deferred and effective features. And the combination can be really interesting. Consider, for example, eClass list, the procedure search. The specification of that procedure, as shown by the header comment here, is that it's going to start from the current cursor position, and it's going to move the cursor to the first position where X, the argument, appears. And if X does not appear at all, then it's going to move after. So we start at the current cursor position, and we see at the next position if X appears, at the position after that one, and so on. And we end whenever we have either found X or exhausted all the possible elements that could contain X. If X is found, how do we find out where it occurs? This is a little quiz. Well, the answer is very simple. We can just test index. Index is going to give us the position where X occurs, or more precisely, index is going to give us that position if X does appear in the structure. How do we know after the fact whether X was found? Well, we test after. So typically we're going to test after. If after is true, we know that X did not appear. If after is not true, then index is going to give us the position where X appears, at least the first position after the current cursor position. In terms of the structure, this is a very interesting feature because you can see that search is implemented. It's a do-end, it's not a deferred feature, but even though it's an effective feature, it relies for its implementation on force, which we have seen is deferred, and on after, which you will easily see has to be deferred as well, at least if we treat it as a function. Because the exact way in which we implement after depends, like for force, on the exact implementation that we have chosen for our list. So search is going to loop until either after or item equals X. The or else is important, by the way, because when after is true, item is not defined. So you have to be careful here. And it relies, the loop relies on two deferred features, even though the search procedure itself is not deferred, it's effective. So we have an interesting scheme of program construction in which we have, at a high level of abstraction, high in the inheritance hierarchy, a feature search in class list, which is effective but depends for its implementation on features here after and forth, which will only be affected, only be implemented in descendant classes. It's an interesting form of reuse where the reuse is not of an exact operation but more of an operation scheme. The more immediate form of software reuse, meaning of applying software elements that have already been written, applying them for new developments, the standard form of reuse is to call out to a feature of a class that had been written and the feature is fixed and the class is fixed. But here we have a different form of reuse in which we don't reuse individual implemented operations, but we reuse a general pattern. This tells us, search tells us how to search sequentially in a structure, even if we don't know exactly what the structure is going to be, and the details of what the structure is going to be are, of course, given by force and after in descendant effective classes. So it's a really interesting form of software reuse, which enables us to combine reuse with adaptation. We can describe a feature such as search also as a form of don't call us, we'll call you. What I mean is that unlike cases in which we call out to a reusable element which performs a certain function, the basic form of reuse, here we have more a general scheme, for example, iterating over a structure, and we reuse that scheme, but for the individual elements of that scheme, descendant classes are going to fill in the holes. This is also the general idea that is applied in the design of the EiffelBase library. What is EiffelBase? It's the fundamental library of data structures that you have coming with Eiffel. So it contains all the classes that we use for standard data structure applications, stack implementations, array implementations, list implementations, queue implementations, and so on. And what you see in this figure here is the top of the EiffelBase hierarchy, entirely made, except for the lowest level, of deferred classes. So you see that the most general notion is the notion of container, and then there are notions like box, like hierarchical, like linear. For example, linear describes the general notion of a structure whose elements can be accessed linearly, sequentially, one after the other. You also have, as another example of a deferred class, the notion of table, which is very general and has many different variants. So all these top classes of the inheritance hierarchy are deferred, as indicated by the asterisk, because they describe high-level, incompletely specified, or at least incompletely implemented abstractions. And then at the bottom, you start finding specific implementations like hash table, for example, or array, which are effective. And of course, this is only part of the inheritance hierarchy, and there are many more effective classes. So you see how we use the notion of deferred class as an abstraction mechanism and as a taxonomy mechanism. As another related but different application of deferred classes, we can use them to model systems, very general systems, not necessarily software systems, not necessarily programs. Of course, these descriptions could lead to programs later on, but they're just a way to model some system, some part of the world. So here, for example, we have, as part of a chemical plant description, the notion of vat. A vat is a kind of tank. Actually, this is what we say here by using inheritance. Now, this is an academic description. I'm not claiming that it comes from a real chemical plant, but the ideas are important. What characterizes a vat? Well, it has queries, like there's an input valve and an output valve. You can also find out if it's full. You can find out if it's empty. These are Boolean queries. Then it has a current gauge reading. There's a maximum possible capacity, which is also the maximum possible gauge reading. We can empty the vat. There's also a command fill, whose purpose, as expressed by the comment, is to fill the vat, so we're not going to implement it. This is all modeling, this is all description, there's not even any software involved yet. So we make it deferred, but we can express its abstract conditions. For example, in order to fill the vat, you have to have the input valve open and the output valve closed. And as a result of filling the vat, the input valve will now be closed, the output valve will again be closed, and is full will be true, where is full is the Boolean query that tells us whether the gauge reading is at the maximum. And indeed, an invariant of the class tells us that is full is true if and only if the gauge reading is between 97% and 103% of the maximum. The numbers are of course arbitrary, but you see the idea. It's to use deferred classes, modeling through object-oriented techniques, to model some very general kinds of systems which may or may not be directly connected with software, and the ability of using deferred features and classes, in particular the ability to attach contracts to these deferred features and classes even though there's no implementation, is particularly interesting. So what we've seen is a really powerful concept, deferred classes and deferred features, a mechanism that enables us to express concepts and their abstract properties, concepts in a very broad sense, concepts, mechanisms, all kinds of aspects of a software system, independently of any implementation concern, but remaining at the proper level of abstraction.